Thank you for tuning in to the episode 3.6 of Parallel Programming and Optimization with Intel Xeon Phi coprocessors video course. In this video, we will cover the basics of offload using shared virtual memory. It can be used for sharing complex pointer-based data structures.
In the shared virtual memory mode, data movement between the host and the coprocessor is automated. The programmer uses special memory allocators and special offload calls which allow the runtime system to automatically transfer the data from the host to the coprocessor and back. Furthermore, pointers to dynamically allocated objects have the same values, meaning addresses on the host and on the coprocessor. Let's take a look at an example code. This application multiplies matrix A by vector B and computes the sum of the elements in the resulting vector. We will offload the function multiply then add to the coprocessor. First, let's run this application on the host to verify that it produces the correct result. To offload function call multiply then add using virtual shared memory, we need to mark up all the data used in the function as well as the function itself with qualifier silk shared. This will put the variable that follows in the virtual shared memory space. Because array A is referenced by a pointer, we need to make the pointer itself shared and also tell the compiler that it is pointing to virtually shared data. To do that, we put two silk shared keywords. One goes in front of the word double and applies to the pointer itself. The other goes before the variable name and marks the contents of matrix A as shared. Function bodies that will be called from the coprocessor must also be marked up with silk shared keyword. Now let's make sure that the memory for matrix A is allocated in a special memory region, which virtually shared. To do that, we replace the standard allocator malloc with a special allocator offload shared malloc. Now we have marked everything that must be virtually shared with the coprocessor. Now we have to tell the compiler to actually offload our calculations to the coprocessor. All we need to do for that is put the keyword silk offload in front of the function call. Now let's try to compile and run the code. To make sure that the application is in fact using the shared virtual memory model, let's look at offload report. Note that this programming approach requires at least offload report equals to 3. If we want to convince ourselves that the application did in fact offload the function, we need to put in a check using ifdefmic preprocessor macros. With this, the application will print an error message if the offload fails. When we run the application, the correct result is returned without the error message. For the final test, we will run the application with offload devices set to none, so that the offload fails, and here we see that we do in fact get the error message saying offload failed. We were able to offload our calculations to one coprocessor, but we did not have to indicate how to move data between the host and the coprocessor. The compiler and the runtime system took care of data movement for us. Now let's try to offload this function to all the available coprocessors. First, we will add offload.h header file to the included files. This header file contains several offload runtime routines that will be useful for this step. After that, we will add a print statement inside the function multiply then add that prints out the ID of the coprocessor that carried out the computation. To query the coprocessor ID, we use offload getDeviceNumber. To determine how many available coprocessors are currently installed in the system, we use offload number of devices and store it in numDevices. Then, using numDevices, we will iterate through the available coprocessors with a for loop offloading to each. The keyword silk offload cannot specify which coprocessor gets the work, so we instead use silk offload to I to offload to coprocessor number I. We expect a different result when we offload to multiple coprocessors. Because we sum the same outputs, we expect it to simply be multiplied by numDevices. When we compile and run the code, we see that we get the correct result and that in fact both coprocessor 0 and 1 received work. Note here that the print statements are not printed in order. The standard output buffers on the coprocessors are not automatically flushed until the end. Now, although the work was carried out on both coprocessors, the offloads were not concurrent. Silk offload is a blocking call, so coprocessor 1 did not get work until coprocessor 0 finished its workload. To make the offload asynchronous, we add the keyword silk spawn in front of the offload call. Silk spawn is a part of multi-threading framework, or C++ language extension to be precise, called Intel Silk Plus. We'll discuss multi-threading and Intel Silk Plus in later videos. For now, the important idea is that Silk Spawn makes offload non-blocking. When we run the application, we see that the result is wrong. The sum is equal to 0. This is because we started the offloads, but forgot to wait for them to finish before we printed the result. To fix the issue, we will use the keyword Silk Sync. This will wait for all functions launched with Silk Spawn in this scope to finish. When we compile and run the code, we now see yet another wrong result. This time, the issue is what is called a race condition. Data races are a very important topic in parallel programming. We will deal with them several times in this course. What happened in our code is multiple coprocessors try to update the variable sum at the same time, which leads to unpredictable results. To fix this, we can have each coprocessor write to a different location. Let's change variable sum to an array sums of length num devices. Each coprocessor will write into different element of array sums. However, instead of passing in another dynamically allocated array, let's have the function return its result. To get return values from offloaded functions, we simply assign the returned values to the corresponding location in the result array. Note that both Silk Spawn and Silk Offload is on the right-hand side of the assign operator. Finally, the host will add up the individual results stored in sums to find the total value sum that is reported. Now, when we run the application, we see that the race condition is resolved and we get the correct result.
In this episode, we covered virtual shared memory model. In the next episode, we will see how to asynchronously offload to the coprocessor and use CPU as well at the same time, and how multiple Intel Xeon Phi coprocessors can be simultaneously utilized. Thank you for tuning in, and I hope to see you in the next episode.